Okay, so you should go to the lockdown browser and go to Blackboard or course and start the practice quiz. And I would actually set the Zoom to focus mode as well. So throughout the exam, you should stay in your seat. And if you have a question, you can use a breakout room so that you just say that you have a question, and then we will move you to a breakout room. But right now, I don't need to set that up. The start code for today's exam is 4861. For the practice quiz is 4861. So then you can start. It will have 3-minute timer. There's only 2 questions, so hopefully we can finish that quiz quickly. When you finish, please signal to me with your hand so that I can or face the camera, or that's good. So I can see whether I can verify your verify that your submission on Blackboard. I can see some of you have finished. Okay, that's good. How do I verify that on Blackboard? Oh, I can see. I can see a score on Blackboard. Okay. So at the time, on Thursday, when you finish your exam, I think some of you will be able to finish early. After you submit your exam, do not leave Zoom. Okay, you need to show me a hand, or then I will give you a go ahead and to leave if you want to. Because we need to make sure that the exam is submitted before you leave the Zoom session. Is time up for everyone now? I think now, yeah, I can see. I'm not just going to say it one by one. I'm just going to, today it's, you all finish at the same time. It'd be hard to say that. So on Thursday, we will let you go after we verify. Oops. Wait. Okay. Just a second, there's trouble some here. I've accidentally set some of you as co-host. Anya, it works now for you? Okay.
Yes,
Okay,
it
now
works.
it works. Yeah, okay. I think you all finished. So now I think that's okay. Anyone having trouble with lockdown browser? Anyone? Any questions before we go back to the main session for the class? Okay, so for some of you, we didn't test the webcam setup, like Manyi. So on Thursday, we will have to set up the webcam at a different location so that we can see both you and your screen. And there shouldn't be a virtual background also on that day.
Okay.
Okay, and Alice as well. Okay, now you can go back. You can quit the Zoom on your second device and then log back on your computer. We'll start with the exam, with the class. So I give you a minute to go out and come back in on a different computer now. Same Zoom link. And yeah, that's it for you as well. Thank you.
Okay, then see you on Thursday.
Yeah. See you. Okay, I see people are coming back. Still, please turn on your webcam if you can, if you want to. It does feel good when I can see many of you. So it feels like teaching to a group of people rather than just a bunch of black boxes. Okay, I could start sharing my screen and then we can get started. Okay, so again, this is the exam will be on Thursday at the time of the class. Please join the Zoom session at 11:15. It's important for you to come at 15 minutes early than the normal class time because we need to use that time not only to check your webcam positions, but also to take screenshots of your student IDs. The exam will cover these 5 chapters, as I talked about before: scales of universe, motions in the sky, reasons for seasons, phases of the moon and eclipses, nature of light, matter and their interactions, and the sun. As I said, that you need to set the webcam in such an angle so that it can see both your computer, you, and your desk, the desk space in front of you. And so you need to use a second device, and it's better to put it at a small distance away from you, but slightly behind you so that it can see the screen. And it should not be looked high or low. Arrive early so that we can take screenshots of you and your student ID. You need to hold your ID close to the camera, and also that in the same screen that we can see you, and we will take your screenshots of you and your ID, because I don't recognize all of you yet, so that is the trouble with Zoom meetings, but so that's why we have to check ID carefully. You're not allowed to use any notes, books, or calculators. You can use blank paper, but the paper needs to be blank, and you can use a pen and paper. simple calculator is available on lockdown browser so that you can, if you need to do any calculations, you can use that within the browser. No need for another calculator. So except for the device you use for the exam, and the Zoom proctoring, put all the other tablets, phones, electronic devices away out of your reach. So if you have a second screen or a third screen, you can put it into black mode or close it down so that it's not, it doesn't cause any suspicions. The test will have 30 multiple choice questions, and you will have 45 minutes to complete it. The time should be more than enough that some of the questions are quite easy, so that you probably will finish within 30 to 35 minutes even. But you have 45 minutes to finish it. There will be a timer just like the one you saw in the practice quiz, so that it will tell you how much time is left. And at the end of the exam, you do have to submit the answers yourself by hitting the submit button. Otherwise, it will not submit. Do not quit the browser before you submit. I'll give you a start code at the start of the exam that's different from what I give you today. And for the whole test, you need to stay in front of your computer for the whole duration and do not leave during the middle of your exam. So you should go to bathrooms or whatever and drink water beforehand. Do not basically plan to stay in front of a computer for an hour. If you have questions, you can speak up and we will place you in a breakout room for you to ask questions. Actually, one thing we didn't test is to keep your audio on so that we can hear, but yeah, we didn't test that. I think if you can, you're in a quiet environment, you should turn on your audio, enable your audio enable your microphone so that we can hear the background, so that you don't have to touch your cell phones during the exam, and you only need to say that I have a question and my name is blah blah, and I will place you in a breakout room so that we can answer your questions without disturbing anyone else. Once you submit your answer, close the browser, turn around and face the camera, and we will verify your submission on Blackboard and then let you quit Zoom. Do not quit Zoom before we verify your submission. Okay? That's it. Any questions? Oh yeah, there's, I will give these formulas on the exam so that on the exam, at the top of the exam, under the descriptions of the exam, there will be these formulas given for it so that you don't have to recite these, but I'll be you only need to know what these symbols mean. Like C means speed of light, and lambda is wavelength, and F is frequency, these things. And then I'll give these to you so that you can use them for your exam. There's no difficult calculations involved. Maybe one thing I forgot here is E equals MC squared. I also didn't include that equation, but E equals MC squared, that is the one that I forgot to include. But that's okay. I think that should be easy for you to remember. Okay, any questions about the exam? Okay, so now we're going to continue to talk about serving the stars, measuring radius and mass. So we have talked about several things. So actually, so I'm going to start a Zoom poll, and then for you to answer this question. Please answer this question on the poll on Zoom. This is a review question for last lecture's content. Same question here on the screen share. Okay, that's all we have answered. So I'll just end the poll now. And you can see most of you got it correct, that since star B is 3 times further away than star A, so then its luminosity is going to be 9 times higher because it's distance squared, because they appear equally bright in the sky. So that the correct answer is E, is 9 times 10 to the 26 watt. You answered this question during the quiz. I didn't quite see your results, but I will just talk about this quickly. So the correct answer is type M is the coolest temperature. So among all these different spectral types, M is the coolest one because it is at the end of that spectral type sequence. What about the hottest? If I change it to hottest, what would that be? Let me start the poll again. Which spectral type is the hottest star? Okay. Time is short, so I will just cut it now. So most of you got it correct. The type O is the hottest star because the sequence goes from O, B, A, F, G, K, N, right? So there's many mnemonics that make it work. So the most common one is, oh, be a fine girl, kiss me right now, right? Kiss me. And so, or be a fine guy, kiss me. And so it's always the start is the first one and M is the last one. Why is the spectral type sequence of stars not alphabetical? We had this question during your quiz, and the correct answer is B. It's because the original alphabetical labeling did not correspond to surface temperatures and had to be reordered. The original alphabetical labeling is ordered according to the strands of the hydrogen features, but it turns out the hydrogen strands is actually not strongest at either the hottest or the coldest end. It's the hydrogen feature is strongest at the intermediate temperatures. And astronomers have to reorder the spectral type so that it form a continuous sequence in the strands of the spectral lines. And that is happen to be the temperature sequence going from hottest to coldest. So that is OBA FGK. Okay, so in the past 2 or 3 lectures, we have learned how to measure distance of stars, and we do that by measuring the parallax. We have talked about how to measure luminosity of stars by using the inverse square law of light. And then last time we talked about how to measure the temperature of stars by taking the spectra of stars and looking at the spectral feature and determine the spectral type. Once you have the spectral type, then you know the temperature of the stars. So today we're going to talk about how to measure the sizes of stars and how to measure the masses of stars. So the first thing is mass. How do we measure the mass of the sizes of a star? How do we measure the diameter of a star? Stars are very, very far away. Although they're big, some are even bigger than our sun, some are smaller. Anyway, they're much bigger than the Earth. However, that they're so far away that they all look really, really tiny in the sky. It's not easy to measure the angular size of stars because they're just too far away and look too tiny. And we can, even using the largest telescopes, we cannot resolve the sizes of stars. It is too small an angle for us to resolve. And you may say that, for example, in this picture, some stars look bigger and some other stars look smaller. Why is that? Is that telling us about the size of the stars? Not really. In this picture, although it looks like some of these stars look bigger, it's a bigger spot in the image, it's actually just because they were brighter. These stars look bigger on a photograph because they're bigger, because they're brighter, not because they're bigger. The reason they look bright is that they make get saturated in the middle, and so the light kind of spill out to the larger radius, and so that you see it occupy a larger footprint on the photograph doesn't mean it is bigger in the sky. It's just it looks bigger because it is brighter. We cannot really using the sizes to measure stars. If you look using your eyes through a telescope, they all look like it's all a tiny dot, and all those dots are exactly the same size. And that size is not determined by the size of the stars. It's actually determined by your telescope or the atmosphere of the Earth. And the atmosphere of the Earth actually smears the image of the light from a star to make it look like a round circle. But that round circle doesn't represent the size of the stars. So how do we know that some stars are bigger and others are smaller? You probably have heard astronomers saying red giants or white dwarfs. And what do we mean when we say red giants and white dwarfs? The word giant actually means those stars are bigger, are huge compared to the sun. And when we say white dwarfs, those dwarfs actually mean the stars are much smaller in size compared to the sun. So we have some ways of telling the size of the stars and how. And the way we tell the diameter of a star, the most common way is actually to use the laws of radiation. So we talk about the laws of radiation. We talk about two laws of radiation. One is the Wien's law, right? Wien's law tells you the peak wavelength of the black body radiation spectrum is related with temperature. As the temperature goes higher, it gets smaller. The peak wavelength gets shorter, right? So that is one way to measure the temperature of stars. And there's another law, which is called the Stefan-Boltzmann law, that talks about the flux on the surface of stars that is proportional to temperature to the fourth power. This is what we call the Stefan-Boltzmann law. Actually, this will be tested in the exam. That's the Stefan-Boltzmann law. Well, so how is this related with the diameter of a star? We can actually use the Stefan-Boltzmann law to measure the size of a star. And the way to do that is that you first measure the temperature of the star by taking a spectra, measuring its, figuring out its spectral type, then we know the temperature. And you also know the luminosity by measuring the brightness of the star and also its distance, and then you can figure out luminosity, right? So once you have temperature and luminosity, we can actually use the Stefan-Boltzmann law to derive the total surface area of the star. And once we know the total surface area, we can derive the diameter. Because the Stefan-Boltzmann law says the flux on the surface of the star is proportional to temperature to the fourth power. And what is flux? Flux is the amount of energy radiated per unit area. So if I cut a unit area here, like a small area on the star, and how much energy is radiated from this unit area, that is proportional to temperature to the fourth power. That is F. The amount of energy per unit area is F. And then the luminosity tells you what is the total energy emitted by the star. And so that the total energy must equal to the energy per unit area times the total amount of area, right? So that is F times A, that is the luminosity. So since F is sigma T to the fourth, that we know, and luminosity we also know. Once you know luminosity and temperature, you can invert this equation and derive the surface area of the star, so that if I divide both sides of this equation by sigma times T to the fourth, I get area equals to luminosity divided by sigma T to the fourth, right? And so that the area, it can be derived using this equation. And we know that the star is a sphere because that is the best form when it is under its own gravity. It will always want to take the shape of a sphere. And once you know the surface area, you can derive the radius of a sphere, because the surface area of a sphere is equal to 4 pi times its radius squared. So from the area, I can derive the radius, and once you know the radius, you can figure out the diameter. These two are trivially related by just a factor of 2, right? So diameter is 2 times the radius. So from this derivation, I will be able to tell the diameter of a star. So it basically starts with knowing temperature and luminosity, and temperature tells you the flux. And once you know the flux and the luminosity, you can figure out the surface area. Once you know the surface area, get the radius or the diameter. So this is the process of how we measure the diameter of a star, is that you first need to take a spectra or use Wien's law to measure the temperature. And from temperature, you use Stefan-Boltzmann law to get to the surface flux, that is the energy per unit area emitted, and you know the luminosity somehow. And once you know this two, you will be able to figure out what is the total area from which the star is emitting. That gives you the diameter. But how do we know the luminosity? Luminosity is known by measuring how bright the star is using a light meter on Earth, right? And also figuring out its distance using the parallax measurement, right? By measuring how the star is shifting around over a year relative to its background stars. And then we can figure out the distance. And once you also measure the brightness of the star using a telescope and a light meter, so this brightness is also flux, right? It's the amount of flux we receive on Earth. And so that once you know these two, you can also derive the luminosity. That is basically this flux times another area. This area is a different area. It's the area of a huge imaginary sphere that is centered on the star, with the radius being the distance between us and the star, right? So this is what we talked about last time, right? Remember this? And you actually see that these two processes, there are some similarities, right? Recall the measurement of luminosity. How do we measure luminosity? Remember I said that if you look close to a star, you get a very high surface flux, right? Because the light from the star is spread over a very small area, or a small sphere. And if you are very, very far away from the star, then the light is spread over a much larger sphere. And what you get at the telescope will get smaller, right? Because the flux you get is the amount of energy per unit area at the place of the telescope. But if the telescope is far away, the flux is spread over a very large imaginary sphere, so that per unit area, the amount of flux gets smaller and smaller the further away you are from the star, right? That is the inverse square law of light. And you can see this actually is a very similar process as the way we determine the size of the star, right? In this process, luminosity equals to the energy we receive per centimeter square times the surface area of this imaginary sphere. So it's flux times area. It's also flux times area, but this flux is different from the surface flux of the star, and this area is also different from the surface area of the star. It's basically that when we are measuring this at far away distance, the surface area of this imaginary sphere is much larger, and the flux at this sphere is much smaller, but the product of them is the same. It's still the same luminosity of the star. And in this expression, when we calculate the surface area of this imaginary sphere, we are using 4 pi r squared, and that radius here, the radius of the sphere, what we call d here, is actually the distance between us and the star, right? And not the radius of the star itself, but the distance between us and the star. So you see that we actually use this L equals F times A twice in two different contexts, right? When we go from the brightness of the star and the distance of star to luminosity, we use L equals F times A. That F is the F flux we're measuring at a distance away from the star. And that correspondingly, that surface area, that area is this area of this huge imaginary sphere, right? And that is because I say it is huge because that imaginary sphere, its radius is the distance between us and the star. And that huge sphere with a huge area and the tiny flux give you the luminosity. This is L equals FA. But in a different context, we use the same equation, the same physical laws actually, to measure the radius or diameter of the star. And here that this is also L equals F times A. But this flux is the surface flux on the star's surface, where it is really, really hot, right? The temperature is really high. And you use Stefan-Boltzmann law to figure out what is the surface flux of a star. This F is huge because it's really, really bright if you're on the star, right? That flux is huge. But the surface area is much smaller than the other area, so that because you are at the star surface, this flux has to be at the star surface, and this area is surface area of the star. So that you can see that although it's in both contexts, it's L equals F times A, the F and A are different. The two F's are different in these two contexts. The two A's are different, and the F and the A has to correspond to each other. Where you're measuring the F, you should also measuring the A at the same place. But these two things are the physical laws behind them is the same. It's basically flux times area give you luminosity. And luminosity for the star is an intrinsic property of it, so it does not change. I hope this explanation helps you to connect these different processes together, and seems the simple equation is actually very fundamental in astronomy. It connects many different measurements. Okay, any questions? So now let me pose this question. I'm not going to set a Zoom poll, but I'm just going to ask you, and you can respond either by speaking up or type your answer in the chat window. So two stars have the same diameter but different temperature. So star A is 3000 K on its surface and star B is 6000 K on its surface. Which star has a higher luminosity? Okay, star B has a higher luminosity because it has a higher temperature. That's right. Because when its temperature goes up, flux goes up, and so the luminosity goes up. So luminosity goes up with temperature to the fourth power, and because they have the same diameter. Hotter stars is more luminous. What about this one? Two stars have the same temperature but different diameters. Which star has a higher luminosity? A or B? They have the same 3000 K temperature. Which star has a higher luminosity? Please answer in Zoom or by speaking up. Okay, thank you, Hangyi. Star B has a higher luminosity because that's correct, because it has a larger diameter. Thank you, Trinto, as well. So that star B is the one having a higher luminosity because the surface area is larger, and the two stars have the same temperature, so there's no difference here, and that causes luminosity to be bigger. So larger stars is more luminous because they have larger surface area. Then suppose a star has a higher luminosity despite its low temperature. What can you say about its diameter? If it has a huge luminosity, but a very low temperature, what can you say about its diameter, about the size of the star? Please type in Zoom or speak up. Thank you. Some of you answered, Hanyi answered, it is going to be very large, huge size. Thank you, Chen Zhi and Trinto as well. Yeah, it is a big fat star, right? Because if temperature is low, but luminosity is high, then that means the area has to be high in order to compensate for the low temperature, but not only just compensating for the low temperature, but also have to overcome the reduction of flux caused by the temperature. So the A has to be super, super large, because as temperature decreases, the flux decreases very fast because it's going as temperature to the fourth power. So the area has to be also become bigger by a huge amount in order to overcome the reduction of temperature to give the star a high luminosity. So this is a huge, huge star. It has to be a huge star, it has to be very large diameter in order to overcome the small temperature. And so this is actually what we call a red giant. Red giant stars are actually cold stars, but they have huge luminosity because they have a huge surface area. So those are giant stars. What about a star has low luminosity despite high temperature? If it has low luminosity but high temperature, what can you say about its diameter? Again, please answer in Zoom. It has to be a tiny star, that's right. Small size, that's correct. So if the temperature is high, luminosity is low, so the area has to be super small in order to compensate for that and to make the luminosity small. So this is what the star would be, and it has to be really, really tiny, and this is what we call a white dwarf. The star has to be a very small diameter. So this is how we know that red giants are giants and white dwarfs are dwarfs, because a red giant have a high luminosity but a very low temperature, and so its diameter must be huge. And white dwarf have a low luminosity but high temperature, so its size must be small. So that's the most common way of measuring diameter of stars, but there's also another way of measuring sizes of stars, and that is using eclipsing binary stars. What is an eclipsing binary star? An eclipsing binary star is made of two stars. It's a binary, so it's when you have two stars orbiting around each other, we call it a binary star. But what is an eclipsing binary star? The eclipsing binary star meaning that the two stars happen to be aligned, that their orbital planes are in the direction, facing us. So when we look at the two stars, when they are orbiting around each other, one star will get in front of another, and then at another time, the second star will get in front of the first star, so that they are supposed, like in this picture, that if this small star is orbiting this big star, you sometimes, when they are not eclipsing each other, you can see two stars. But if they're eclipsing each other, then you can only see one of the stars. So one star is blocking another, we call it as eclipsing happening for the two stars. Basically, one star is blocking part of another star. Just like when the moon blocks the sun, from our view, we say it is a solar eclipse, right? So eclipsing binary stars are just doing this so that we can actually see the amount of light variation. So you measure the total brightness of the whole system as a function of time. Sometimes you will see two stars. For example, if this second star is at the on the side of this big star, that you see both the red one and the blue one, you see the total amount of the light from the two stars. But when this small size star go behind the big one, even though it is small, it may not be less luminous. It can actually be more luminous. That's possible. When it goes behind the big star, you get a dip in the brightness because you're only seeing the amount of light from only the red star, not the blue one, right? So you see that the brightness of the total system decrease a lot. And then when the star get out, you recover the total light from both stars. And when the small star blocks the big star, you can see it actually blocks only a little bit of the big star, so that there's not a lot of light that is lost, and so you get a small dip in luminosity, in brightness, so that because a part of the red star gets blocked, so that you will have some decrease in the total amount of light. But it's not as much as when you're losing a whole star, right? So that this is, and also it's because of this is a red star and that is a blue star. The surface flux of the two stars are very different, right? Although that in both times you're losing the projected area of this much, when the blue star is behind, you're losing more because it is a blue star. The per unit area is giving out more light, right? So you're losing more here. But when the blue star is in front, what you're losing is an equivalent area on the red star that is being blocked, because the red star has a lower flux, so you only lose a little bit. So that is why the light curve is varying as the stars orbiting around each other, and you see this pattern repeats over and over again. At a certain time that you will see the brightness change, and so this is what we call an eclipsing binary. And in these kind of systems, we can also have another way of measuring the radius or the diameter of the star. And the way we do that is to observe to measure this time of this eclipsing phenomena. So when one star is going in front of another star, you will see the light dip, right? And so that when they're not blocking each other, you see the total light from both stars. And when the second star is going in front of the big one, you start to eclipse it when the edges touch. And so this is what we call the first contact. And then when the blue star is moving that way and it covers bigger and bigger part of the red star, and then when it completely got in front of the red star, that covers the most that it can cover. And so you see that the light dips to the bottom. And then as it goes from between 2 and 3, the amount it covers does not change, so that this part of the light curve is flat. The brightness does not change with time during this period. And when it re-emerges from the other end, actually not re-emerge, when it stops blocking it, when it moves away from the front of the red star, the total brightness recovers back to the original level, where you have the total light from 2 stars, right? So this is the first, second, third, and fourth contact. And you can see that from first to second contact, how much does the blue star move? It moves its own diameter, right? But from the first to the third contact point, it moves the whole diameter of the big star, right? So that by measuring the time interval between the first and the third contact, we can measure the size of the big star. But here, all we get is just a time. We only measure how much time it takes for the blue stars to go across the big one. We don't get the size yet. To get the size, not only you need to know how much time is spent in front of the star, but also you have to know how fast is the blue star moving relative to the red one. So we have to have another way of measuring the velocity. Then we can use the equation distance equals velocity times time, right? You know the time, but you have to know also velocity to know how much distance that the blue star has covered. And that it tells you how big the red star is. So how do we measure velocity? We can measure velocity using Doppler effect, right? So that this again is something that we will test in the exam that you have talked about before. These things we use it over and over again in astronomy. Because you have a star that if this blue star is going around the red star, and you are looking at it from the Earth in this direction, When it is in front of the star, you don't see the motion is tangential to us, so we don't see a Doppler effect. But when it is on the side, you will see the spectral line of this star shifts around, right? Because it's moving, when it is on this part of the orbit, it's moving toward the Earth. When it is on this part of the orbit, it is moving away from the Earth. So if you take the spectra of the star B, of this blue star, you will see that the spectral line sometimes shift towards the blue side, sometimes it shifts towards the redder side. And by determining how much it shifts, you can figure out the orbital velocity of the star B relative to star A. And then once you know the velocity, and you measure that time interval between eclipse, between the first and third contact point, then you can use this equation to measure the diameter of the big star. So to combine the velocity with the eclipsing time measurement to obtain diameter of a star. So this is another way we quite often use to measure the size of the stars. Any questions so far? Okay. So that's the size of stars. How do we measure the mass of a star? That's the last thing for surveying the stars. The mass of a star determines the strength of its gravity. So in order to measure the mass of a star, we have to use something that is related with gravity, and that because gravity determines the motion of an object orbiting a star, so we need to measure the motions of orbiting objects, and that will reveal the mass of a star. That is according to the universal law of gravitation. And this is related with Kepler's third law. Some of you may have heard of this, others may have not heard what is Kepler's third law. That's okay, I'll explain that. Kepler's laws are about motions of planets. And in particular, Kepler's third law says that more distant planets orbiting the sun, they are orbiting the sun at a lower average speeds compared to the planets that are closer to the sun. Like the Mercury is the closest planet to the sun, right? Earth is the third closest. And then other planets like Jupiter, Saturn, Uranus, Neptune, they're even further out. And these planets, they're orbiting the sun at different speed. Some of them are orbiting faster, others are orbiting slower. So some are having a short orbital period, others have longer orbital periods. What Kepler found is that the orbital period is related with the size of their orbits. So you can use P to represent the orbital period of a planet, and use the R to represent the orbital radius of a planet to the sun. Then you have this relation between P and R. It's like the square of P is proportional to R to the third power. Or in other ways, you can see the sign means proportional. This means that as R increases, as R to the third power increases, P square also increases with the same proportional amount. And another way is just saying that P square is a constant times R to the cube, R to the third power. Okay, and K is constant here. And so this is a figure illustrating that. So the y-axis is R in astronomical unit. I did not talk about astronomical unit before, but here I just briefly mention it. Astronomical unit is also a distance unit. It is a distance, average distance between the Earth and the sun. So you measure planets' orbital radius using the astronomical unit, and you measure these planets' orbital period in Earth years. Say, how many Earth years does it take for Jupiter to orbit around the sun? It takes about 12 years for Jupiter to orbit around the sun, 12 Earth years. And so if you take R to the third power and take P to the second power, these two things are proportional to each other. They're very well correlated. And so what is this K? what is this? What determines this K? This proportional constant K actually reflects the strength of the gravitational force on the planet. And what determines the gravitational force on the planet? It is the mass of the sun. So how it is related? The proportional constant K is actually can be expressed as in this formula according to 4 pi squared divided by G, which is the gravitational constant, times the sum of the sun and the planet. So basically the total mass of the sun and the planet. But the planet is much smaller than the sun and is much unimportant than the sun in terms of mass. Most of the mass in the solar system is on the sun. So we don't have to worry about the second term. It can be basically ignored. But so you can see that with Kepler's third law, as long as you can measure the orbital period and the orbital radius of a planet around a star, you will be able to derive its mass of the mass of the star. So this is basically how we derive the mass of other stars as well. So you don't have to know how this equation is derived. This equation is derived using Newton's universal law of gravitation. So if you actually do the physical derivation for that, then you will be able to figure this out from the universal law of gravitation. But here we're just going to use this as a result to tell you how we measure the mass of stars. All you need to do is measure the period and the radius. And sometimes the planet's motion around the star is not in regular circles, it is in an ellipse. So if it is an ellipse, then there's no way to define radius. In that case, we use the semi-major axis of the ellipse, and that this equation is still valid when you use the semi-major axis. So we just need two things, the orbital period and the distance between the planet to the sun. So that is how we measure the mass of the sun. But for other stars, it is actually very difficult to obtain these two things. You have to detect planets around other stars. Now we have detected planets around other stars, but those measurements, it is easy to measure the orbital period, but not easy to measure the distance. So it is actually still not trivial to use this method directly on other stars. What is possible to measure masses of other stars is to use binary star system again. So that in a binary star system, like the eclipsing binary system I talked about just a few minutes ago, it is actually possible to measure the mass of stars because these motions of the binary stars relative to each other can reveal their total mass. So for example, in this case, this is the Big Dipper. You can recognize the second star in the Big Dipper, called the star Mizar, is actually a binary star. And this is a very well-known binary star. Sometimes you can actually see that if you have good eyesight, you can actually see the second star in that. It's very thin compared to the big star, and then compared to the brighter one. But some people with good eyesight can actually see the second star in there with their naked eyes. And in that case, it's actually two stars orbiting around each other. In that case, we don't see, it is not an eclipsing binary, but we can actually, because the two stars can be visually separated, if you take photographs of the system over many years, you can actually see that the star orbiting around the other, just like in this case. And so that from that, you can measure the orbital period and also measure the distance between them. Once you have both the orbital period and the distance, you will be able to figure out the mass of both stars. And in another case, the star Albireo, this is in the constellation Cygnus, and this is also a binary system, and the two stars are orbiting around each other in elliptical orbits. and you can actually see you can measure the orbital period and distance to measure the masses of the stars. And also in eclipsing binary systems, it's also quite easy to do this, as we talk about, so that you can see, you can use the light curve of a star, basically the brightness variation with time, and you can see what is the total period of the system. So from the first time the blue star gets behind the big star to the second time it gets behind the big star. So this whole thing that tells you what is from this point to that point, this gives you the orbital period of the system, right? This how much time has lasted between these two big dips will give you the orbital period. And once you know the velocity from Doppler effect, as I mentioned before, you can also figure out how large a distance it has covered, right? That is the distance of the orbital diameter. And if you just need to divide that by 2, you can get the orbital radius of an eclipsing binary. And once you figure out the radius and the period, you will be able to calculate the mass of the stars. So this is how we measure masses of stars. But basically, masses of stars can only be directly measured in these binary systems. So that having binaries is very important for measuring some properties of stars, like the size and the mass. But a lot of stars are in binary systems. Actually, about half of the stars, or more than half of the stars, are in binary systems. So these systems are not rare. So it's actually possible to find a lot of them. So now we have reviewed, so we have talked about how to measure different properties. We have talked about how to measure temperatures, luminosities, diameter, and mass of stars. This table shows you what kind of range can these properties vary between, so that, for example, what is the range of temperatures a stars can take? The coolest stars can be as cool as 2000 K, and the hottest stars can be about 50,000 K or even slightly hotter, some of them. And this is a range about from the largest to the smallest values is a factor of 25 to 1. Luminosity can vary by a much larger amount, because not only luminosity goes as temperature to the 4th power, it also goes with size squared, right? So that if you have a high temperature star, but also much bigger, you can have huge luminosity. So you can see the luminosity can have a huge range from 0.0001 times that of the sun to 100,000 times that of the sun. So here, when we measure luminosity, we are measuring it relative to the luminosity of the sun. So 1 means a star has the same luminosity as the sun, and 100,000 means that the star's luminosity is 100,000 times that of the sun. But you can see from the least luminous star to the most luminous star, the difference is 1 billion to 1. So this is 10 to the 9th power. So this range is much, much larger than the temperature range, than the dynamic range of temperature amongst the stars, right? This temperature is only 25 to 1, but luminosity can go as 1 billion to 1. And diameter and mass are these ranges. The diameter goes from 0.01 times that of the sun to about 1,000 times larger than the sun. And mass is about 0.1 times the size of the mass of the sun to 100 times the mass of the sun. So stars can vary by a huge amount. And our sun is actually a very, very average star. It's very, its temperature, luminosity, diameter, and mass is all somewhere in between. It is very average, very typical. Not the coolest, not the hottest, not the biggest, nor the smallest. And it's just an average star. So what is the largest star that we know about? That is this star in the Canis Major. It's called Vivae Canis Majoris. It is the largest star ever known. It is a red hypergiant. its diameter is about 2,000 times that of the sun. So if you put the sun next to the star, you cannot even see it. You have to zoom in this little box where you can find the sun. This is how big the sun is compared to that star. And then you place the Earth's orbit around here, that you can see that the star is way bigger than the orbit of the Earth around the sun. So how big can it be? If you put that star Vivae Canis Majoris in our solar system at the position of the sun, this star itself will cover the orbit of Saturn. So everything within the solar system, from the sun, Mercury, Venus, Earth, Mars, Jupiter, and Saturn, will all be inside the star if you place it in the solar system. And its mass is about 30 to 40 times that of the sun, and its luminosity is about 450,000 times that of the sun. So it's the largest star that we know about. Okay, so that summarizes this chapter about surveying the stars. So we learned about how to measure different properties, and so that will prepare us for understanding stellar evolution that we will continue after a break. So now let's take a 5-minute break and return here at 3:45. You can take a bathroom break now. See you in 5 minutes. Okay, now let's come back. We'll talk about the next section of this chapter. Actually, we didn't finish this chapter yet. The next section of this chapter about surveying the stars is about the Hertzsprung-Russell diagram. This is the perhaps one of the most famous diagram in astronomy. So you know what is called the HR diagram. It's Hertzsprung-Russell diagram. Of course, it's some diagram is named after two astronomers, Hertzsprung and Russell. But what do we mean by this? So first, to understand this, why we are making some kind of diagram, let's think about how you study stars. How we study stars is just like how we study any other subjects. If you, whenever you study a class of things, like say animals or something, you always want to first determine their properties and then look for relationships among their properties. For example, in this picture that's showing the evolution of the horses, you can see the bones of these fossils of ancient animals and modern horse, and you also age date these bones to different geological times, and then you try to see whether there's a correlation between the shape of the bones and the geological time sequence, right? That is how you figure out the evolution history of the horse. Just for anything that any kind of things that when we are trying to study a class of these different things, you have to basically determine properties of them and then look for relationship between those properties. From that to deduce origins and see how they change over time. And what do we mean when we say relationship between properties? Let's take an example using human beings. For example, for us, heights and weights are very two fundamental properties. Some people are tall, other people are short. Some people are heavy in weight, some people are light in weight. And so there's some natural variations between heights and weights for us. And so if you measure heights and weights for a group of people, then you can try to see how they are related. Are these two quantities related? When we, from our experience, we know that they're certainly related, that on average, heights and weights are related. Taller people are usually heavier. And so that is according to our conventional wisdom. But in order to make a more accurate study, so that you will actually want to gather some data, you sample a large number of people and you measure their heights and weights, and then you can make a graph to see what is the average relationship. And on this graph, each point on a graph will represent the height and weight of one person. So for example, I sample 100 people and then measure their height in feet and measure their weight in pound. And then you can put a bunch of points on a graph showing this height versus weight. And some people are very tall and heavy, and some other people are very short and light. But there are also other people who are short and heavy. It means they're overweight, or other people who are tall but light, that are relatively light. That means they're very thin. And so if you plot these things, this diagram will show that the points are not randomly distributed on this diagram. If you plot height versus weight for 100 people, you will see that actually there is a correlation between these two quantities. What do I mean when I say there's a correlation? You can see this is just a bunch of scatter points. What do I mean when I say there is a correlation? You can see, although there is a lot of scatter in this plot, it is not completely random, right? It's not completely random. That because, for example, there are very few points over here, very few points with very few people with very tall height and very light weight, and also very few people with who are very short and also heavy. And so there are actually not many people in these areas of this diagram. And most people are correlated. Most people the points are distributed diagonally in this plot. And that's what we call there is a correlation between the height and weight for people. That when people are taller, they tend to be heavier. So this is what we mean by a correlation, and this reveals the relationship between properties. For people, that this actually varies quite a bit, but the stars are actually much more regular. Stars are actually simpler than human beings. And if you plot the luminosity and surface temperature of stars and plot all the stars on this diagram, you find that the distribution of stars on this diagram is not random at all. There is several regions where stars are concentrated. For example, you can see there is a diagonal relationship that it goes from the upper left of the plot to the lower right of the plot. Luminosity on this axis is given in unit of the sun. So that is 1 means 1 times the solar luminosity, and here 1,000,000 means 1,000,000 times the solar luminosity. Here is very low compared to the sun in terms of luminosity. The horizontal axis is giving the surface temperature. And you can see I'm also marking it with the spectral types from O, B, A, F, G, K, M. So this is from the hottest star to the coolest star, right? So this is so the temperature is hot on the left side and cool on the right hand side. And you can see for most stars, they actually follow the diagonal zone. That stars that are really, really hot are also very luminous. Stars that are cool are also very less luminous, are very, very faint. And also there's giants over here, red giants and supergiants and white dwarfs in these regions. So you see it is not uniform, randomly distributed. And this is the diagram that we call the Hertzsprung-Russell diagram. This is, or HR diagram for short. This diagram is very important for understanding the evolution of stars. It is basically showing the luminosity versus temperature of stars. And how we make this diagram, according to what we have learned, you just need to measure the luminosity and temperature, right? Because that's the 2 axes of this diagram. How do you measure luminosity and temperature? To measure luminosity, you have to know how far away a star is and then measure its brightness, right? And then you can derive its luminosity. And then for other stars, and then to measure temperature, you need to take the spectrum and then deduce the temperature, right? So we can only make this diagram for the stars that we have spectra with, and also the stars that we know the distance, because without distance, you will not be able to measure luminosity. If you have distance, then you can measure luminosity easily. And if you have spectrum, then you can measure temperature. So over in the beginning, in the first half of the 20th century, astronomers was able to measure distance to a lot of stars and also take spectra for a lot of stars. And then from these data, they can measure the luminosity and temperature. And for each of these stars, you can draw a single point on this diagram of luminosity versus temperature. And then once you put all the stars down on this diagram, you find their distribution is like this. So this is a real HR diagram. You can see each crosses here represent a single star. This is a star. This is a diagram that is made using modern data, using the data from the Hipparcos satellite, which measured very accurate distances using parallax, from which we can derive a very accurate luminosity. And then you can plot luminosity versus temperature. You can see that the distribution of stars indeed are not random, that there's a diagonal distribution. It goes from the upper left to the lower right, and then there's some stars on the upper right corner and the lower right corner, lower left corner. And this is what we call the regions of three regions of the diagram. the most important feature in this is mean sequence. And you can see that the majority of stars actually distributed over here. As you can see in this diagram, you can see there's some number of stars on the upper right corner. You can almost count them one by one. You can also count the number of stars in the lower left corner, bottom left corner, that is also countable one by one. But if you're trying to count the stars in the middle, you can see that the density of the points here are very, very high, especially in the lower half of this diagonal distribution, right? So this here, the points overlap each other and they almost saturated. So this is where the majority of stars are. The most stars are distributed over this area. And this is what we call the mean sequence of stars, the mean sequence on the HR diagram, on the Hertzsprung-Russell diagram. And this mean sequence tells you that when the stars is hotter, they're more luminous, and when it is cooler, they're less luminous. Right? Because remember the direction of the axis, that on the horizontal axis, hot is on the left side, cold is on the right-hand side, and the y-axis is luminosity from faint to bright, faint to luminous. And this is always the way we draw the HR diagram. We almost never flip the axis. So just remember the direction of the axis, and then you draw down the sequence. You will know hotter stars are more luminous, and this is what we call the mean sequence, because 90% of stars are distributed over here. And what is setting this relationship between luminosity and temperature? This tells this mean sequence, the existence of mean sequence for the majority of stars means that luminosity and temperature are very tightly correlated. Why is hotter stars more luminous and cooler stars less luminous? What is setting that is actually a stable nuclear fusion, because as I said, when we talk about the sun, that you have to have stable nuclear fusion in the middle, right? It is actually set up by gravitational equilibrium, because gravity is trying to pull things towards the center, and it's the central pressure that is trying to push against the gravity. And it sets up a balance, which we call the gravitational equilibrium, and that keeps the center of the stars hot, and where you can have nuclear fusion. And when a star is formed, it will always form a stable nuclear fusion rate, so that the rate is just maintained, so that it generates a certain amount of pressure to balance against the gravity. And this balance is ultimately set by the mass of the star. So the mean sequence is actually a mass sequence. As you can see labeled on the diagram, the upper left corner of the mean sequence, these are massive stars. And the lower right sequence, the cool and less luminous stars, those are very, very low mass stars. So the reason for this is just gravitational equilibrium and energy balance. And that is what is dictating that mass is setting that is what dictating that mean sequence is a mass sequence, because more massive stars have a hotter temperature in their cores, because they need this higher temperature and higher pressure to push against their own gravity. So when they have a higher temperature, they are going to be able to have very fast nuclear fusion, right? Because as I said before, that in order to have nuclear fusion, you have to overcome the repulsive electric force between protons, right? To push the two protons together so that they can feel their strong force between them. And so if you have a hotter temperature in the core, you're going to have a much faster fusion reaction rate. So when you have a faster fusion reaction rate, you generate more energy per second. And that will mean that you have the star has to radiate faster, right? Because all these energy that's generated in the middle have to be radiated out. Otherwise, the star is going to become hotter, right? Whatever energy that is produced per second in the middle have to be radiated away on the outside surface by the star into space. So that if you generate more energy per second, you have to radiate more energy per second. When you radiate more energy per second, that means the star is much more luminous. So more massive stars have hotter cores and makes them more luminous. And less massive stars do not have very strong gravity, so they do not need a very high pressure inside, so they do not need a very high temperature inside, so their core temperature is much lower. And because their core temperature is lower, they don't have very high fusion rate because they cannot push these protons towards each other very easily, so that you will have a lower fusion reaction rate, so they produce less energy per second. And since they produce less, they also radiate less. So that means they radiate slower. We call them less luminous. So this is the why that the more massive stars are hotter and also more luminous. So they occupy the upper left corner of the HR diagram. But less massive stars, they are cooler and also less luminous. So they occupy the bottom right corner of the HR diagram. And so that is why the other stars are in between, and there is a sequence from the upper left to the bottom right. And this is where most of stars lie. This sequence is actually the hydrogen fusion sequence. All these stars are in their cores, they're turning hydrogen into helium through nuclear fusion. So all of these stars are fusing hydrogen into helium. And more massive stars, hotter in their core, they're brighter intrinsically. When I say brighter intrinsically, I don't mean they look brighter in the sky, right? It's brighter measured by intrinsic luminosity. And less massive stars, they're colder in their core, they're fainter in terms of intrinsic luminosity. So the more accurate term here is not brighter and fainter. More accurate term is more luminous and less luminous, right? Less massive is colder and less luminous, and they're also colder on the surface, and they also tends to be smaller in size. And more massive stars are more luminous and also hotter in the core and hotter on its surface, and they are also bigger. Because they're hotter on the surface, they will look blue, and the less massive stars, because they're colder on the surface, they look red, right? Remember that Wien's law, that when you have a red star, it's going to be colder than a blue star. And so that is why in the HR diagram, that on this side we use red colors, and on this side we use blue and white colors. You can see this is also a color sequence going from blue stars to red stars in the HR diagram. So because hot is blue and cold is red. And we try to keep the color coding consistent with the color of the stars here. So that's the main sequence of stars. I think let's talk about this just a little bit more before we end today's lecture. So there is also a very tight correlation between the mass and luminosity of stars. We can measure the mass from binary stars, as we said before, and luminosity we can derive from apparent brightness and distance. When you plot these two quantities against each other, you find the luminosity is very tightly correlated with the mass of the stars. So this is expressing the luminosity in terms of the solar unit. So this is luminosity of the star divided by the luminosity of the sun, and 1 means the position of the sun. And here, horizontal axis is the mass, also divided by the mass of the sun. 1 means the mass of the sun. And you can see that most stars are tightly correlated with each other. You can see there's very little scatter around this line. And it turns out the luminosity is proportional to the mass to the 4th power. And this mass luminosity relation implies the massive stars have shorter lives compared to low mass stars. Why is that? Because more massive stars have more hydrogen to fuse into helium, right? But its luminosity is going as mass to the fourth power. So the luminosity increases much faster than the amount of mass, the amount of hydrogen it has. Although massive stars have more fuel, but they're burning it much, much more quickly because the lifetime of a star is derived by the total amount of hydrogen for fusion, that is what we call fuel here, the total amount of hydrogen for fusion, and that is proportional to the total mass. It's always about 10% of the total mass of hydrogen can be turned into helium. And so the lifetime of a star is determined by how much hydrogen you have for fusion divided by how fast you are consuming it. And the consumption rate of the hydrogen is reflected by the luminosity, because all that hydrogen that is turned into helium produces a certain amount of energy, so E equals mc squared, right? And so that is all radiated away by the luminosity of the star. So once you do this, you get the lifetime of a star. The lifetime is determined by mass divided by luminosity. Because luminosity is proportional to mass to the fourth power, so as mass increases by a factor of 10, luminosity is going to increase by a factor of 10,000. So the lifetime is going to be shorter. So because a star that is 10 times more massive than the sun will be 10 to the 4 times more luminous. And so that it has 10 times more fuel to burn, but it's burning it at 10,000 times faster. And how will its lifetime compare to the sun? It's going to be time divided by 10,000. So that will mean that the lifetime of this star that is 10 times more massive is going to be much shorter than the lifetime of the sun. It's going to be 1,000th lifetime of the sun. So sun has a lifetime of 10 billion years. So that star, if it is 10 times more massive than the sun, it's going to have a lifetime that is 1,000 times shorter. So it's going to be 10 million years. So more massive stars actually live a much shorter life on the mean sequence. So these more massive stars on the upper left corner of the mean sequence, you can see their lifetime is actually short. And our sun can live a lifetime of 10 billion years. But these stars that are more massive than the sun only live like 10 million years. It's still a long time, but compared to the time scale in the universe, compared to the time scale of most stars, this is actually a very, very short amount of time. These stars are burning bright and hot, but they're not going to last very long. It's easier for a star to last longer if they're burning it very, very slowly. For the stars that are actually much less massive than the sun, they can have a much longer lifetime than the sun. So that's the end of today's lecture. So this is what we are going to continue to talk about next time. We'll talk about red giants and white dwarfs, and also talk about stellar evolution using the HR diagram. That's it. Thank you very much.
Thank you. Bye-bye.
Thank you. Bye.